if we don't record. So let's go ahead and get started with this. So let's see. So today is we are going to continue by doing what I like to do, which is basically we're going to revise all the stuff that we just learned last lecture, right, on Wednesday. But we're going to go through it with the slides for the textbook. Now, I like these slides. They've done pretty well. And these slides are, you can find them on the website for this book. So I'm just simply going to go through them. And again, if you think the slides are helpful, the book's really, really helpful. It's a really good textbook. That's why we switched over to it. So I definitely think you should get it, especially if this is, your first time programming. So building Java programs, this is, again, just what the basic stuff is. So we were talking about basically how computers, they really can only store sequences of zeros and one. And, well, working with sequences of zeros and ones, we're not really geared to do that. I mean, there's a reason why our entire counting systems are almost always base 10, because we're kind of geared to deal with things 10 because we have 10 fingers. But also, like, trying to read all this stuff is really hard. So as a result, we abstract that away and we just deal with this high-level stuff. So we can deal with string, the HI being, actual letters and numbers being numbers. So there are, a bunch of these different types for numbers and text. So integers, we typically use int for integers by default, which means that they go up to 2 to the 31st power minus 1, which was around 2 billion, right? That was the size of it. Y minus 1, where we're going to use, either the positive numbers or the negative numbers need a space. One of them has to give up space for a 0, So that's why you get that -1 in there. But integers, remember, those are the whole numbers. Doubles we use for real numbers up to 10 to the 308th power, which is an obnoxiously huge number. And remember, those are doubles are 64 bits. These are 32 bits, so 4 bytes and 8 bytes each. Characters are just single pieces of text, but again, these are like single bits of text. It's a bit faded because it's faded on my side. But again, that's just really a single letter, which are tedious to work with. If you're working in C, that's how you work with most of your most strings. You do it letter by letter. But here we're just going to, we skip straight to using strings. But the important thing about characters is that they're really just ints underneath the surface, which we'll see when we do some cryptography. Because basic code breaking is really fun. And again, the basic stuff, and when I mean basic, I mean the stuff that we used until the past maybe 150 years ago. Until about 150 years ago, did it actually get really complicated and hard to understand. It took about that long for us to figure out how cryptography worked. And then Boolean. Those, again, are, if you're taking your math concepts class, we're going to do a bit about Boolean values here, which will be much easier than in your math concepts class. Why do we distinguish between real numbers and integers? Because, they answer different questions. And because integers, the math, it works out better. So anyway, everything in Java basically is expressions. And the most basic expressions are these kind of things, which we'll have a quiz on this week. So examples of expressions are operations like this: 1 plus 4 times 5. And remember, this will be evaluated according to PEMDAS. Parentheses first, then exponentiation, and then multiplication, division, and all the rest. Now expressions do exist that are really simple. This 42 over here is technically expression. It's very easy to evaluate this expression because there's no operations going on. So that's the simplest expression, which we call a literal value because it literally is that. And complex expressions basically can be as complicated as you can imagine. and probably more so. Because we can always make an expression more complicated by just adding another number. Or adding another expression to that already existing expression. So again, here's our 5 binary operators, meaning that they take one operation. And binary meaning they take 2 different arguments, right? We use addition, subtraction, or also you can throw a negative sign in front of something and make it a negative something. So that's why they say or negation. Multiply, divide, and then we use the modulo operation, which we learned about last time, which is simply the remainder. Right? It's actually a bit more complicated than that, and there's awesome things you can do with this. But for right now, it's best to think of it as a remainder operation. Right? So it evaluates these expressions as you run it. 1 plus 1 would be evaluated at 2. System.out.println would print 3 times 4. So how would we actually print out the text 3 times 4 rather than the expression? Well, the way we do that is, of course, new class, browse for source folder, classroom, intro code, okay. Finish. So how do we actually, right, the question that was asking is, right, system.out.println gives you all this jazz. So if we want to print out 3 times 4, well, first I'd have to actually hit the right keys, run it, and we get 12, right? But if we literally wanted to print out 3 times 4, we can just throw that into a string, and it will print out this literal value. Okay. Again, this is just a reminder that integer division, when we're dealing with just integers, we have to go back to 4th or 5th grade when we didn't know how to do decimal points, which is that basically we're just going to divide stuff and only have the whole portion of the quotient, and then we'll have a remainder. So, right, 14 divided by 4, that goes in 3 times to give us 12. So this would be 3 remainder 2. So the 14 divided by 4 would give us 3. Same with 45 divided by 10. That's going to give us 4. Okay, which is actually pretty convenient. A little trick over here. 45 divided by 10, right? If you divide something by 10, that's going to give you the number in. If you divide a 2-digit number by 10, it gives you the number in the tens place, which is pretty cool. And if you divide any number by 10, it's going to just, another way to look at that is throwing out the ones place, right? So 45 divided by 10 throws out the ones place, and now that becomes the one place. And that's kind of useful if you want to go through things digit by digit, just dividing stuff by 10. It's very so you might think that this is an inconvenient operation, but there are cases which we'll see, like when we get into problems like, okay, give me a number and then sum up all the digits for me. Those kind of problems, it's very useful to be able to do integer division and just throw away 1 digit at a time. So divided by 0 causes problems when your program runs. So let's go ahead and see that. Right? It doesn't. Right? Just like your calculator doesn't like dividing by 0, your computer really doesn't like dividing by 0. It comes up with this nice big error, exception in thread main, division by 0. Right? And it tells you what line it occurred at. Interestingly enough, that's only for integers. Now, doubles, on the other hand, you get others. Interesting things happen when you divide things by 0.0, right? When you divide doubles by 0. So let's see what happens there. Infinity. It just literally gives me out infinity. So, of course, if I do 1 plus 4 divided by 0, that's going to give me, it's not going to give me infinity plus 1. It just still gives me infinity. What about negative 4 divided by 0? It's going to give me negative infinity, right? And these are just things. Now, this works in any programming language that follows the IEEE floating point notation. Okay, for somebody typically then eventually tries this. What happens if I do 0 divided by 0 with doubles? It gives me nan. What does nan stand for? Anyone? Yes? Not a number. Nan stands for not a number. We don't really have a meaningful way to express this. So we're just going to tell you it's not a number. We can say that 0, the infinity is kind of useful, but nan tells you that it's not. And negative 0.0, that's not going to do anything special to it. I mean, maybe you think it might give you negative nan, but it doesn't. So, all right. So whoops. Don't need a mean to open another thing for Eclipse. All right. So let's go back here. Let's speed up a bit. So precedence, right? This is the whole thing that we were talking about, and definitely where you'll see some questions on your quiz, and definitely some stuff on your first exam, which you should already know this stuff, fortunately. Right? Generally, everything is evaluated left to right, right? 1 minus 2 minus 3 is 1 minus 2, which is negative 1. Negative 1 minus 3 is negative 4. So, normally it just goes left to right, but multiply, divide, and the modulo remainder operation, that has a higher precedence than plus and minus. So, rather than doing, whoops. Oh, I skipped something there. I'll go back to it. So rather than doing 1 plus 3 times 4, which is, and getting 16, instead we'd get 1 plus the result of 3 times 4, which is 12, plus 1, which is 13, right? So here, in this expression, 6 plus 8 divided by 2 times 3, right? We go left to right. So 8 divided by 2 gives us 4, times 3 gives us 12. 12 plus 6 is 18. And just going back here, the results of modulo. So what happens with all these results? Like 45 to mod 6. What happens there? 45 mod 6, right? We can get up to 42 using 6. So 45 divided by 6, that eventually, that goes in, I think, 7 times, and that gives us a remainder of 3. 2 mod 2. Well, there's no remainder after a number's divided by itself, so we get 0 here. 8 mod 20. That gives us 8 because you can't divide 8 by 20, so you end up with just a remainder. 11 mod 0. Ooh, interesting one. Let's go ahead and evaluate that one. Division by 0 exception, right? You're trying to ask, what's the remainder after we divide 11 by 0? Well, we can't divide things by 0, right? Cannot divide integers by 0. So we get an exception there. All right. So just like interesting thing, just like getting rid of, just like we can successfully divide to get rid of the last digit, we can get the last digit of a number by modding by 10, right? So this big number mod 10, that might be a kind of question you might get asked on exam because it's not actually that hard. I'm just asking for the last digit of this. What's the remainder of this divided by 10? It's the last digit. Dividing by 10,000 gives you the last 4 digit. And a trick we'll use a lot is that we can mod by 2 to see if a number is even or odd, right? If it's divisible by 2, so if we mod something by 2, it's divisible by 2 if the remainder is 0. Okay. There's no real need to go over these precedence questions. You kind of know them already. The only thing, we'll go over this one, though, because it has mod in it. So 1 times 2 gives us 2. Then we go left to right. 3 times 5 gives us 15. Then 15 mod 4 gives us 3 because the fit remain right. Because how big can we make 4? How many times can we multiply a number by 4 until we get to a number that's less than 15? But get it as big as we can. That gives us, we can multiply 4 by 1, 4 by 2 to get to 8, 4 by 3 to get to 12, and we can't get any bigger than that. So 15 minus 12 gives us 3. Then 2 plus 3 gives us 5. Okay. So real numbers, examples of this are 0.22, negative 42. Oh, and we can do scientific notation as well. 2.4143 times 10 to the 17th power, right? That E for scientific notation. We can make numbers, we can take any integer value and turn it into a double manually just by putting 0.0, or even just a point after it will make it a double. Everything still works the same way as integers. The only difference is that what happens when we combine them. Yeah, there's no real need to go over that. When an int and a double get mixed, the result is a double. So 4.2 times 3, that 3 gets converted to a 3.0. Okay, so the important thing is that it's not for the entire expression, though. It happens basically on a case-by-case basis. What that means is that in this expression, see how we have a single double in here? Let's see how this works. 7 divided by 3 gives us 2, right? It doesn't give us, because this is an int, so our result is an integer. 2 times 1.2, we've got an int and a double, so the result of this operation is here is a double, 2.4. Plus 3 divided by 2, again, these two integers are just integers, they're not doubles, so their result is a double. Then we do 2.4 plus 1, so we end up with 3.4. Right? So so this conversion only works on, the conversion only happens for each pair, right? It doesn't happen for the whole thing until, you know, it actually collides with a different type. So again, over here, 2.0 plus 10 divided by 3 times 2.5. So we go left to right and evaluate the higher order precedence. So not 2.0, but 10 divided by 3 gives us 3 via integer division. And then we do 3 times 2.5, which gives us 7.5. And then we do 6 divided by 4, right? And that's integer division, and 4 goes into 6 only once. So we get 9.5 minus 1. Okay? And finally, there's one more type that we convert up to, right? We can convert from ints to doubles. This is the only, there's other conversions that happen. As I mentioned, there's longs as well as ints, right? Which are just told bigger numbers. And you can imagine that conversion, basically an int to a long, works pretty simply. And but it pretty much doesn't do anything tricky to the math, right? Same with a float to a double, that doesn't do anything tricky to the math either. So the only thing where basically we can get where your math might be affected is if you use string concatenation, which basically is just a fancy way of saying, let's glue this string to something else. Okay? So hello plus 42, that doesn't do some weird math operation, it just glues, it turns 42 into a string and it glues hello and 42 together. 1 plus ABC plus 2, that just glues everything together. Now on the other hand, ABC plus 1, so remember, addition is pretty low on the precedence, so it just goes left to right. ABC plus 1 turns it into ABC1, and ABC1 plus 2 turns it into ABC1, 2. On the other hand, right, 1 plus 2 is 3, plus ABC becomes 3ABC. Does that make sense to everybody? Right? It's because we're going left to right. But remember, we have to take into account order of operations. ABC plus 9 times 3 isn't ABC plus 9 times error, right? We do 9 times 3 first because that's higher order than the plus operation. So we get 27 plus ABC plus 27, which is ABC 27. And so what's useful about this is that we can use this basically to put an expression together like this. Okay, so variables. Now that we know how to evaluate stuff, let's talk about variables again. So we have this code here, and what's bad about it? It's not immediately obvious because, again, you just started coding. Our subtotal is 38 plus 40 plus 30. Tax is 38 plus 40 plus 30 times 0.8, right? Assuming we're in 8% tax and a 15% tip. The tip is 1/15 of that value. So the total is 30 plus 40 plus 30 plus 30 plus 40 plus 30 times 0.8 plus 30 plus 40 plus 30 times 0.15. And perhaps you figured out what's the problem with this. after I said it a bunch of times, which is that I'm reusing this. I'm re-saying stuff a whole lot. And that's a bit of an issue, right? Because as programmers, we're kind of lazy people by nature, which is that we hate redoing work. We hate redoing work. I mean, and I mean, yes, people in general hate redoing work, but you know, programmers, if we're dealing with numbers, we want to do something about it. So we can use variables to deal with this. Okay, a variable is a piece of memory that's given a name and a type can store value. Right, and we went through this. Basically, it was the whole int x thing. So we can declare a variable, we can initialize it, and we can use it. So, and a lot of times what we'll do is that basically we'll set aside memory. So I was doing all these things in one step, by the way, when I was going through our program earlier, and I was going int x is equal to 5. It's actually 2 steps there that I'm doing. I'm combining 2 steps into one. The first step is this declaration. And what this declaration does is, let's see if I get there, slides. So what this declaration does is that this sets up a little imaginary box in your memory. This int x, if I say int x is equal to, does the angle work for everybody over there? Okay. And that means I'm creating a little box in memory. It's called x. Okay? Giving it a label x. Okay? That's just simply because I need to give it a label so I can keep, you know, because if I create an int y, right, I need a way to keep this box separate from this box. And right now, they don't really have anything in it. Well, that's actually kind of a lie. What it does have in it is that if you don't give it a value, it's got to come up with something to put in there. So by default, if you don't declare anything, it will have 0 in it. But for right now, you know, assume it's got nothing in it. So that's the first part of this. And this is where we declare a variable. This tells the computer to set up, to put aside 4 bytes of memory for us, 32 bits of memory, so that I can store an int. Then, somewhere else in the code, I can go x is equal to 4. And that means I can take the value 4 and store it in x. Now, it's very important to remember that, as I said last lecture, I was about to say episode, but that I suppose that makes sense with the way I'm recording them. But that the way to visualize this equal sign isn't as like the mathematical equals, but rather as we're taking 4 and we're storing it in x, right? We're taking the value on the right and storing it in the left. And I mean, if you take 2168 with me too, this is something I'm actually going to have to hammer on about in a week when we talk about memory location. We're taking the value on the right, whatever it is, and sorting on left. Specifically the expression, right? Because these are all expressions. This one happens to just be a very simple expression, right? So end result of me running this, executing this, is that I store 4 in here, right? If I change this to a more, conventional expression, so 3 times 3, it's going to evaluate the result of 3 times 3, right? It's going to evaluate 3 times 3 and store it in here. Technically, this does have, there's a precedence table, and this is all one expression. And this expression over here is basically as low as you can get on the order of operations, right? So Java has this giant table that's bigger than PEMDAS, and it's of all these sort of operations and when they can occur. And basically, this one, the storing something, is about as low as it can get, because typically you don't want to store something before you've fully evaluated it. Probably not. And so that's how expressions work. Let's go ahead and get back to here. Okay. Yep, it's not what I wanted to do. Let's zoom through this again. All right. So, and we went through a lot of this. I don't want to present online. I want to, there we go. So the idea here is that once we've created, so we can create this, right? And what we can do is that we can assign values as variables. So that's what this that equal sign is called, an assignment operation. So so here we've got int x is x is equal to 3. We store 3 inside of x. My GPA is 1.0 plus 2.25, so it stores the value of this expression in there. And once and the great thing is that now once we store it, we can evaluate it again and again and again and use it more than once. Okay. Okay. So the cool thing is that you can also it isn't set in stone, by the way. So int x is over here. X is equal to 3. It's equal to 3 here, and then we can reassign the value. So let's see. Let me actually code up an example. Int x is equal to 5. Now here I'm doing both the assignment operation and the I'm doing both the assignment operation and the declaration in the same step. I'm both creating it and initializing it. Okay, so system.out. Whoops, where does it do that? System.out.println x. Now I can say x is equal to 7 plus 2, which is 9. And so it's going to print out that value. Now, of course, one thing that's important to understand is that, remember, I still have this line up here from earlier, right? That's going to crash. When you get an exception, your program stops. It doesn't continue. This is a go to jail, do not pass go, do not collect $200 kind of deal, right? It just stops the program if you have an exception. We'll learn about ways to cause the later on that will cause the computer to just not to just skip over the exception and not crash. But for right now, exceptions cause your computer to crash. So let's not deal with that. So did not mean to close it like that. Okay, so set, yes, hello, code. Okay, so now here, and now lastly, this is possibly the part of programming that I think, so let me run this. Right, so it's 5, and then it's 9. Okay, so you can reassign this. Now this is possibly the trickiest part over here, because if you read the equal sign like an equals in mathematics, the assignment operator like it's an equals in mathematics, this does not make sense whatsoever. But what you need to remember is that the value on the right gets stored on the left. Okay, what's that? Whoa. Okay. Right? This does not make sense in your typical mathematics, like in when we're dealing with algebra, right? X is equal to x plus 2. That doesn't make sense, right? But let's go ahead. But in Java, this means that the value on the left, the value on the right, we're gonna evaluate it and we're gonna store it in the variable on the left. Okay? Let's go ahead and see if it makes Let's go ahead and see if it makes more sense if I just create a different variable for it. Okay, int y is equal to x plus 2. Okay, this makes sense, right? So x is currently 9, right? Plus 2 is equal to, which is equal to 11. So we're going to store it in y. We're going to print it out. Unless I horribly messed up my math, we should get 11, right? So So now, if we do this, x is equal to x plus 2. Which is just taking the value in x. So let's go ahead and work through this. We're going to work through it like it's an expression. So first off, remember what I said. The assignment operator is all the way at the end of precedence. So first we do x plus 2. Well, first I have to figure out what x is. What is x? X was 9, last I checked. So 9 plus 2, that value, so this evaluates to 11. So we take 11 and we store it in x. So we can use a variable to update itself. Now you might ask, why in the world would we want to do this? Because it's useful to take a single variable and just update it. as it goes on. So basically counting up with the variable. It's a very common operation where we say we want to take a value, and then after we do an operation, maybe do this operation on it. X is equal to x plus 1. Say, just increment one more time. It's actually a specific operation. Incrementing. 12. So, that's pretty cool. Okay. Yep. And here it says it again. It's not an algebraic expression. It means store the value at the right in the left. Right, and they have the same example here. Int x is equal to 3. X plus 2, well, that's 3 plus 2 gets evaluated and gets stored in 5. Sorry, and we store 5 in x. So again, we can only store the right variables in the right type. 2.5 can't be stored in x because we can't fit something into here. And same with, on the other hand, we can take a smaller type, like an integer, and we can convert, and it can automatically get converted into a double. So what will happen, double my GPA 4 automatically turns into 4.0. Double average is 11 divided by 2. Well, 11 divided by 2 is 5. And then we're going to store that and convert it into a double, right? Because remember, this is a case-by-case basis here. So 11 divided by 2, those are ints. And then the assignment operation says, okay, we're going to take this and store it, this integer, turn it into a double so we can store it in a double. On the other hand, you can't do it this way because you're going to lose data this way, right? So there's all sorts of errors that can crop up with this. The first is basically that I can't, once I have an x, so this is a declaring a variable. Once I've declared a variable, I can't declare another one. This tells Java, I'd like to set up another variable box and give it the label x. All right, another int, and I'm going to give it the label x. And Java's going to be like, you already have an x. If you give me another x, I'm going to be confused. So we can't do that. So that's one thing. Another thing is that once we create a variable, Java really wants you to make sure that you, actually give me a value for it first. Right? It tells me that y may not be initialized, may not have been given a variable, a value for it. So it's going to compile. So this is what we call a compiler error, which means that if I try to run it, it's going to give me this error exists and it's going to crash. Except we told you it was a crash, right? In fact, we're not even going to run it because, again, you can't. It's going to crash. Now, again, going back to programs crashing. A program will run until it does crash. So remember how we have this at the top to begin with, and it wouldn't even run. If we put this at the bottom, our program will run up until the point where we get the crash. So, right, it will print out all the stuff, and then it will crash at the very end. Okay. Okay. So if we take a look at this one, we can improve this with using variables by saying that by taking that value, the 38 plus 40 plus 30, and put that into the subtotal. Then we can figure out what the tax is by multiplying 0.8 against that value, figure out what the tip is, right? So see how we had all this numerical stuff over here, and then we just simply figured out what our variables were and then used them all together over here. Okay, so variables are really useful for our answers. All right. So again, so now because we've already introduced the fact that we hate redundancy, we're going to talk about eliminating redundancy. So, right, let's go. If we go back to our drawing example, right, back over here. Right, and if I wanted to just do stuff, right, I did this basic thing over here. So I had this whole. I said while you guys were drawing your own thing up, I drew my own thing. So there was this whole X tube over here, right? which I could just paste to make, you know, this part of the rocket ship longer and longer, right? But, you know, first off, it's tedious to build it like this, you know, to do all these operations and copy and paste, right? And not only is it tedious, right, but now I've done it a bunch of times, and I don't know how many times how many X tubes I have, unless I want to actually physically count them. So it starts on line 81. So 1, 2. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've got 12 of these lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've got 12 of these lines, right? I had to actually physically count them to figure out that I had this many X tubes on there. So redundancy is terrible. Or doing this is terrible. Or rather, redundant code, basically just copying and pasting it, is kind of just annoying, especially when that same code just does the same thing over and over and over and over again. So now, you know, the variables and the expressions, those were all kind of, you know, the expressions weren't hard because you already knew them, and the variables, they made sense once we explained them. So this is like now a bit of novel stuff if you haven't programmed before. And if you did Python, this will look a bit different. Okay? And this is the for loop. Got to remember it's Shift F5, not F5. So the for loop allows you to repeat statements over and over again. So here we have Homer says, I am so smart, I am so smart, I am so smart, SMRT, I mean SMART, right? So Java's for loop says, let's just go ahead and repeat this task many, many times. Now, this is, just take this in for a second, because it does look like a bunch of gibberish right now, right? Okay, so we've got this word for, and God knows why that's in there, right? What the heck does it mean? Why are they saying for? Right, we're calling it a for loop, so why don't we put loop down there? I mean, do we really value a letter, you know, a letter that much? You know, one less character? Okay, so let's go through this. An open parentheses, I guess it's okay, and there's a closed parentheses, so I guess this is all part of the body. You know, this is all part of this aforementioned for loop, and I see a curly brace and another curly brace. So considering the way we know curly braces to work, we can guess that anything between these curly braces means that anything in between these curly braces are part of the for loop, right? Okay, even though we don't understand this, right? This must be some like kind of information about the for loop, right? And this curly brace and this curly brace, this must be, you know, whatever's in between these must be part of the for loop. All right, we see an int I is equal to 1 statement, and then a semicolon, and then wait, no, that's not an arrow. That's a less than or equal sign, right? That's a less than or equal to. And an I++, what's that? An I++? So don't worry about it. We'll go into this. But what this does is that this repeats this code and this code down here. These are equivalent. In other words, they will do the exact same thing. Homer says, and then these I am so smarts, this statement will print out 4 of them. So the for loop has 3 portions to it. Yeah, I know, you'd think it would have 4, but it has 3. Or at least 3 parts over here. It's broken up into these 3 parts over here. Initialization, test, and update. So we call this the header, and then anything between the curly braces is the body. Okay? So we perform the initialization once, and then we test to see if it's true, and then we execute the statements, and then we update. So let's go ahead and write one of our own, just to kind of see how it looks. So class. Okay, so let's create a main method automatically, right? Public static void main string args. So we break this for loop down into 3 parts. Well, 4 parts if you include this body over here. Okay, so this is the body of a for loop. Okay, anything in here will get executed each time the for loop executes. Now it's called a loop because it's going to execute again and again. Okay? So we've got now a couple of portions to it. So let's go ahead and create that. So we've got our initialization, got our update, and again, white space isn't going to matter, so I'm just going to space it out so it all hangs underneath the equivalent parts. So initialization, test and update. Okay, initialization. So initialization basically says this is the stuff that executes at the beginning of the for loop. And typically what we do, we set up a counter. Typically we use int I because a lot of the times when, as you'll see later on, we're going to be dealing with indices of arrays, and so we use I for indice. And also because we use I because it's, shorthand for integer, so it's an easy way to remember it's an integer. So there's a lot of reasons we use I. And we typically, and a lot of times we'll set it up as 0, but for learning the for loop, before we figure out why things should start at 0, we're just going to start with 1 because it's easier to read for right now. Okay. So while, so now the test, I is less than or equal to 4. Let's go with 3. And then the update. And rather than doing the plus plus operation, I'm going to do I is equal to I plus 1. Okay. So, all right. The way a for loop works is that when we start a for loop, we go int I is equal to 1. So that starts up the for loop. Basically, we create a variable at the beginning of the for loop. Now, this variable only exists for the for loop if it's declared in here. In other words, if I do system.out.println over here, the compiler is going to yell at me. It's going to say, hey, what are you talking about? There is no I variable. I mean, there you had one, but it only existed for the for loop. So that's an important thing. This I is a temporary variable. It only exists in the body of the for loop. Okay? Okay? Now, once we've created, now the initialization only happens again the first time we encounter a for loop, right? Even though we're going to loop through it a bunch of times, this first statement only happens once. Next, we have the test. Now the test happens each time we encounter the for. We loop around, including the first time, which is that we test if this statement is true. If this is a true statement, then we execute the loop. If it's a false statement, then we're done with the loop. So basically, so long as I is less than or equal to 3, this loop is going to keep running, right? So right now, I is 1, right? So we created a variable. I is 1 right now. And so long as I is less than or equal to 3, which it is in this case because it's 1, we're going to keep running this loop. Now the update statement over here, that happens at the end of every iteration of the loop. Every time we go through the loop, at the end of that, once we get to here, this semicolon, this curly brace over here, we run the update statement, and the update statement just executes. It just happens. And what this says is, remember, this is a assignment operation saying we're going to store something in I. What are we going to store in I? We're going to store the current value of I, and we're going to add 1 to it. Okay? I plus 1. So what this is going to do. So let's go ahead and just mentally walk through this. Int I is equal to 1. So I'm going to go ahead and just in the comments, make something over here so that we can walk through this. I is equal to 1. I is currently equal to 1. Is 1 less than or equal to 3? Yeah, it is. 1 is less than or equal to 3, so we go and execute the loop. Okay, so we're inside the loop now, and we perform all the actions that are in the curly braces. Right now there's just one action, right, because this is a comment, so we kind of ignore it. I'll go ahead and move it to the end, so it's easier to see there. And we'll print out, this is a for loop, exclamation point, because I guess we're happy about it. Okay, we finished the body of the for loop, so now we update. We do I is equal to I plus 1, which means that I's value is 2 now. Okay, so now we go back to the top. We don't do the initialization again because, again, we only do that the first time we experience this. So now we're at, once we do the update, we do the test again at the top. It's 2 less than or equal to 3. Yes, 2 is less than or equal to 3, so we execute the body, print out this is a for loop. A second time, close this. Sorry, get to the end, and now we update again. We'd say 2 plus 1 gets stored in I, so 3 gets stored in I. Okay, so now we test. Is 3 less than or equal to 3? Yes, it is. So now we run, this is a for loop, one more time, and then we update. 3 plus 1 is stored in I, which updates this value to 4. So now is 4 less than or equal to 3? It is not, so we're done with the for loop, and then we'll execute whatever happens after the loop. So this will print out, as soon as I add a semicolon, it will print out, this is a for loop, exclamation point, this is a for loop, exclamation point, this is a for loop, exclamation point, and then done. So this runs 3 times. Now, when you are writing your code, the good karma way to do this, by the way, is to be able to look at this, is to write it in such a way that we can just look at this number over here, and tell you, and this will tell you how many times it will run. Now, this is the good karma way to do it. Now, obviously, since I'm going to be giving you exams, and exams are meant to actually test your reading skills, I am not going to often write it in the good karma way. A lot of times I will just simply write it in a way that you'll actually have to think through it and how many times it's run. But most of the time when we want to write this in such a way that this number over here will tell you exactly how many times we want this to run. Okay, so notice how I have a 3 over here, and this ran 3 times. If I change this to 17, well, let's go with something we can easily count, 7. This will run 7 times. So this is a for loop, 3 over here, 4 over here, that's 7. Great, so this prints out 7 times. If I want to do now 17 times, it's pretty easy. Boom. If I want to do 117 times, no problems over there. And you can make this almost as big as you want it to be. Right? There is a limit to the size, of course, and that is that basically since we are using an integer over here, we can't make this loop run more than, 2 billion times. Right? Now, also, it actually doesn't normally take this long for for loops to run. The only reason it's going to take this long is because I'm printing out this is a for loop, and printing out takes time. If I were to actually comment this line out so that it just kind of churns through the for loop without doing anything, it goes through it a whole lot, very quick. Or if I just wanted to do, if I just had a variable int x is equal to 1, int x is equal to 0, and we put x plus plus over, oh, wait, what's x plus plus? Give me a second. That takes no time at all. But wait, what's x plus plus? Why don't we print out x? X is done, /n. X is x. Done. X is this value over here. Weird. All right, let's see what x is if we do x plus plus over here, what that happens. Interesting. It's 1 more. So, as I've mentioned, we're programmers are kind of lazy, right? And if we see something that happens a lot, then we like to, make sure that we don't have to do it as much. So this is this update operation over here. I is equal to I plus 1, where we just increment something by 1. That's a super common operation because we use it in for loops all the time. So for shorthand, what we do is we write I plus plus, which is a very shorthand operation you can just do with any number. And what that does is that it literally translates to this value. I is equal to, this translates, so x plus plus translates to x is equal to x plus 1, right? It says take the value in x, add 1 to it, store it in x. I plus plus means take the value in I, right? Add 1 to it, and store that back in I. It's such a common operation. It's useful. So hence, that's why we create something like I plus plus. Now, if there's an I plus plus, you might imagine that there's an I minus minus, and you're correct. There's also an I minus minus, which basically subtracts 1. All right. So what else should we? So let's go back to the slides and see. Now that we know this, we can go through this stuff. So here we have an initialization. I is equal to 1. I is less than or equal to 6. I plus plus. I am so smart. Now this example, right? Again, this is being written in the very friendly form where we can just look at it and tell it that this runs 6 times. Now, how do we know that though? Well, this starts at 1, right? So int I starts at 1. It's going to run while I is less than or equal to 6, and the values of I are going to vary. They're going to be 1, then 2, then 3, right? They're always going to go up by 1. So if we've got those many values, I'm going to put this on the board, so sorry you can't see it in the thing, but all I'm doing is just writing out the values. We've got 1, 2, 3, 4, 5, 6, and if we, those are 6 numbers, right? We're going to have 6 different values, so this loop is going to run 6 times. Make sense? This loop goes through the numbers 1 through 6, inclusive. Inclusive meaning that both the 1 and the 6 are in it. Now, this I has a special term, which is called the loop counter. We can use any name. We can use any name. It doesn't have to be I. I is just simply convention. Okay? Now, the test, that can be any Boolean statement you want, but typically it's a less than or equal to, or a less than operator. If we're counting in reverse, it's going to be a greater than or equal to operator. And then, right, here they had the whole shorthands, which are for increment and decrement. Taking a variable and going plus plus is simply saying get the value out of the variable, add 1 to it, and store it in the variable. Take the variable, subtract 1 from it, and store it in the variable. That's minus minus. So int x is equal to 2, x plus plus gives us 3, and we can do this on doubles as well. GPA minus minus is a pretty bad thing to get that happen to you, so don't let that happen to you. There's also a bunch of other shortcuts which are useful to know, and I'll put them back in the express it yourself because they're better over there. Sorry, they're better listed over there. Okay, so let's create an int y is equal to 7. Okay, there's other shorthands for this, right? Because again, modifying a variable by itself is such a common operation. So incrementing by 3, that can be shortened. So that gives you 10, right? Instead, what we can do is this is the same as, we can use another shorthand. Y plus equals 3. And all that does is saying, let's take the value in y, add 3 to it, and store it back in there. I know that seems a bit weird. System.out.println. But that gives us 10 for y. It's just a shorthand. And it's pretty easy to remember how that works. And there's one for every single operator. And there's no tricks here. It's simply minus equals to subtract 3. If you want to modify it by subtracting 3, so instead of 7, we have 4 now. You can multiply it by 3 to get 21 times equals. And divide equals, which will give us 2. And finally, mod equals, which is just simply take 7, mod it by 3, store the remainder in y. Right? So all those expressions just, those are all shortcuts. And like in in a table like this, it looks kind of overwhelming, but really it's not. These are just pretty simple shortcuts. In fact, I find students find these sometimes easier to understand than this version. Right? Now, figuring out this kind of stuff. Now, doing this is actually kind of useful for like mathematical operations. So here's an example where basically we're trying to do some math operations. 1 squared is equal to 1 times 1. 2 squared is equal to 2 times 2. 3 squared is equal to 3 times 3. And we're just printing them out. We're trying to do all the exponents, right? You know, that are or all the squared. So the idea here is that we want to create this kind of loop. Sorry, we're printing these all out one by one, and copying and pasting this kind of stuff is annoying. So what I'm going to do is I'm going to instead write a for loop to do that. So let's go ahead and remember. So I'm going to use I again, but remember, I was something I could just throw away, right? I created in the for loop, so once the for loop's done, it doesn't exist. So in this for loop, I can also create an I if I had both of them uncommented. So for int I is equal to 1. Starting from 0 is the standard way to do it, but for right now, for learning, a lot of people find it I guess the textbook authors found it easier to start from 1, which a lot of you who have already programmed are possibly rolling your eyes, but bear with me because, believe it or not, in some languages, arrays do start with 1. So I is less than or equal to 10, I plus plus. So what is this going to do? Well, the first thing you want to do is, like, if you're trying to figure out what this code does, is the first thing you do is you basically figure out how many times is this loop going to run and what are the values it's going to iterate over. Okay? It's going to iterate over, the values are going to be 1, 2, 3, 4, 5, and you're like, okay, then it's going to go up all the way to 9, and then it's going to go to 10, right? And once I hits 11, though, the loop's not going to execute, right? I will will bump up to 11, and then it won't execute, so that's not a value inside the loop. So even though I does temporarily become 11, we don't write it down because that's not going to be one of the times the loop runs. So this is 10 numbers over here. Well, it's technically, yes, it's 7 numbers and a couple dots, but it's 10. So there's 10 different values that it goes through. And rather than just printing out, the same thing over and over again in this loop, out print line I. So rather than printing out like foo each time that I run this, right? I don't have to print out the same thing each time I go through a loop. I can actually use the variable inside the loop, so the loop counter, and print that out. So now I'm going to print out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? That makes sense because I said all the values for I are going to go 1 through 10, right? So now actually what I can say is I can start using this to recreate the problem. So the way it worked was I squared is, so right now I can print this, and now it says 1 squared is, doesn't make sense to have that over there, 1 squared, 2 squared, 3 squared, and so on and so forth. And what you get is you get all the way up to 10 squared, and then it stops after that, right? Of course, we actually need to do the squaring operation now. So easy way to figure out. So now notice how basically the first time we run the loop, it's for I is equal to 1. We print out 1 squared is. Then we update to 2. So then we print out 2 squared is. That makes sense to everybody? But then we print out, then it updates to 3 and prints out 3 squared. So here's a bit of another, so the format of the loop isn't the hurdle I find for most people. It's the thinking abstractly about that I value. Basically that I can represent any value between 1 through 10. But it's not any value. It's the values 1 through 10 in sequence. It doesn't, like, it's not going to be 5, then 1, then 3, then 2, then 4, right? It's going to go in order, right? Imagine if it didn't. It'd be a nightmare. We'd have to run this a bunch of times until we got the right combination. Right permutation, and that would be, 10 factorial, which would be way too many times to run this program. Okay, so I squared is, and now we can go I times I. So this says I squared is I times I. So when it's 1, it's going to go I squared is 1 times 1, which is 1, and that's going to glue the 1 to this. So I'll need a space just so I can do this. Then I need, then when it updates to 2, it'll go 2 times 2, which will be 4. Then it will be update to 3, and it'll be 3 times 3. So let's run this. All right, that's cool. So we get, and this makes sense. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 49, 64, 81, and 100. Okay, let's go ahead and make this a bit nicer to format, though, because, right, it's not exactly even. And tabs are very useful for doing basic formatting. There's other ways to do it, like using the print format statement, but this way is pretty nice. I can just use the tab to indent everything over. Right, and it lines up slightly cleaner. Okay, so tabs are your friend, right? /t is just a tab. So that's cool. Okay, back to slides. Okay. So, right here they have it's the same thing, only they put theirs in parentheses, just because. For int I, so a way to read this is for each integer I, from 1 through 4, which is now why we call it the for statement, because we're saying for each of these integers I, and the values of I are 1 through 4. And the way I like to remind myself, it's 1 through 6 inclusively. 1 through 6. Right? Because less than or equal to over here. Right? And that's important, that inclusivity. Right? Because if I don't have the less than over here, right, it's going to go up to 8, I plus to 9. 9 is less than 9. Sorry, 9 is less than 10. And then when I do I plus and get I gets to 10, it's going to go 10 is less than 10. So this one will only run 9 times because 10 is not less than 10. 10 is less than or equal to. So this only runs 9 times if I have less than rather than less than or equal to. If I do I is less than or equal to 2, less than or equal to 10, well, it includes the 10 in there. Right, so if you don't want to include that last number, you toss out the you can just toss out the equal sign. All right, so for those of you who need a flow chart, right? Here's a flow chart for it. We perform the initialization once. We ask, is the test true? If it is, we execute these commands in here. All the statements inside the curly braces, which are right now, we've only been doing 1, but we can do more than 1. We then do the update, and then we, again, come back over here. Is the test true? Well, 2 is less than 4. Execute, update to 3. 3 is less than 4, less than or equal to 4. Execute, update to 4. 4 is less than or equal to 4. Update. Execute. Yeah, so 4 is less than 4, execute, update, 5 is less than or equal to 4, that's not true, so no, execute the statements that occur afterwards. So 1 squared, 2 squared, 3 squared, 4 squared, and then after that, we update, I becomes 5, 5 is not less than or equal to 4, so we just stop at that point and execute the woo after that for loop. So we can have multiple statements over here, which, as I implied earlier, it's very useful for drawing. So here we do I is equal to 1, I is less than or equal to 3. So this is the values 1 through 3. I++. So iteration 1, we print this out, which is, inward facing slashes, and then we do outward facing slashes. So that's 1. And then we go to iteration 2, inward facing, outward facing. Go to iteration 3, inward facing, outward facing. And then we're done with that. So then we increment I to 4. 4 is less than or equal to 3. That's not true. So we output the last line. All right. So now let's go and just practice on some. So again, a lot of these are not going to be like but occasionally you're not going to get nice ones. Sometimes we want to do something like here's a good example. For int I is equal to 1, I is less than or equal to 100, I plus, let's actually go with I is less than or equal, I is equal to 5, I is less than or equal to 100, I plus equal to 5. Right, so we're not doing I++ here. So what are the values that we're going to be using here? Well, we start I as 5. Is 5 less than 100? Yes, it is. We execute what will be in here. Increment 5 to 10. Then 10 will become 15, and then 15 will become 20. And so, right, this goes up by 5s because that plus equal 5. Right, and this is going to go all the way to 100. So this is printing out the values 5 through 100. Right, and by 5s. So system.out.println I. So that one's a bit hard to figure out. That's okay. So we get 5, 10, 15, 20, 25, 30, 35, 40, on and on. And we go on and all the way up to 100. That's fairly straightforward. Yeah? Okay. Here's one that's a bit annoying though. So now let's think through this, okay? Because I find it best when we work through these things to think through this. Now, say we wanted to, a lot here we've just been doing counting down. But as the I minus implied, counting down is sometimes an important operation you might want to do. Especially if you're doing the typical thing for that is like a rocket launch, So let's think about how to do that. How do we count down from 10 to 0? Well, so let's go with int. So let's go with 4. Int I is equal to, let's start, so we want to do a, we got to think our way through this. So first, if we want to count down from 10 all the way to 0 inclusively, right? Let's go ahead. How should we do that? Well, the first number we want to start at is 10, right? And so that becomes our initialization statement. So int I is equal to 10. And we can do something other than I here. We can put count, right? Because we're counting down. Int I is equal to 10. And then where do we want to start? The stop. We want this to be inclusively. We want this to be 10 through some number. I is less than or equal to, right? Because we want to include the 0 in here, right? And then rather than going up, we want to go down. I minus minus. Yep, I am. And it's a very common thing to forget, which is that basically that you sometimes forget what you set your variables to. System.out.println. So let's go ahead and print out our count. And we print out, and it works as expected. 10, 9, 8, 7, 6, 5, 4, 1, 3, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So let's go ahead and add a bit to it. Now, let's go ahead and ask ourselves, though, for a second. When we do the t minus a countdown for a blast off, do we include 0 in that or not? T minus 1, then blast off? Do we include the 0? I don't know. I haven't had the opportunity to watch too many launches, but let's assume that T minus 0 is a bit silly. We don't want 0 in there, right? Instead of saying 0, we want to print out blast off at the very end of this. System.out. Sorry, what was that? Yeah, I want blast off at the very, when we're done with the for statement. So if I don't want 0 to be included in here, remember, I just snip this out and say, so long as this number is greater than a 0, we're going to execute it. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, right? Then we'll do count minus minus. Count will become 0. 0 is not greater than 0, so we're done with the loop then. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, blast off. Sounds more correct. Okay, now a very common mistake when you do subtract, so this is the most common mistake that I see, and it's very easy to fix because you know it goes wrong as soon as you do it, right? Very common mistake that I see is to accidentally, if you're going backwards, you accidentally put plus plus instead of minus minus, right? You go up rather than going down. And this is a bit problematic because this is what we call an infinite loop, right? It's counting up, and all those numbers, they're greater than 0, right? So it does seem, now your first inclination is that this will run forever, right? Okay, right? Because these just keep going up. Okay, so now it would take us a bit too long for me to show you what actually happens by just printing out the number, so I'm going to terminate it. But, 3 million is definitely greater than count, so we're going to execute the statement, and then increment it to another number that's above 3 million. So this is what we call an infinite loop, where it just keeps going on and on and on and never going to stop. Although in this case, let's go ahead and comment this out and see what happens. It stopped, right? It completed the for loop and then hit blast off. So sometimes infinite is a bit unaptly named, but what the heck happened there? Okay, what in the world, right? It kept going up and then it stopped. So let's go and trace back our steps for a second. What is the biggest, remember, does anybody remember about what the biggest integer is that you can store? About, right? I don't need the exact value. So, what's the range around? Is it the millions or the billions or the trillions for an integer? Billions. It's about 2 billion. It's about 2 billion and a bit. So let's go ahead and system.out.println, and again, the way I just figured out, integer.max value, which is the biggest integer value you can have, right? So we had 647,483. So we had 2.1 billion. Okay, that's a lot. That's a pretty big number, but that's not an infinite value, right? So what happens when I add 1 to this value? So I added 1, and it then became a negative. All right. Now this has to do with the way that that binary numbers are stored in Java, or basically in binaries numbers are stored. Period. And it's actually a very amusing story. So let's go ahead and I'm going to deal with basically 4-bit numbers, right? So first thing to know is that basically, remember what I said, is that basically when we're dealing with binary numbers, that initial 0 is used for positive or negative numbers. Now, positive numbers, so everybody thought, since we need positive numbers, we thought, okay, I'll deal with 5-bit numbers, with 3-bit numbers right now. So we've got the positive minus place, we've got the 8s, so we've got the, not the 8s, but we've got the 4s place, the 2s place, and the 1s place, right? So this number, for instance, would be, this is 5, right? Because this is 4 plus 1 is equal to 5, right? This is a binary number 5. Okay. Now the first thought was, okay, how do we store binary numbers? First thought was, let's just go ahead and put a 1 here if we want this to be -5. Okay. The issue is adding these numbers together. If you add a positive number and a negative number together, they should nullify. So if I added in +5 plus -5, it doesn't result in what I'd like it to, which is 1 plus 1, which is 0, carry the 1, 1. 1 plus 1 is 1. So 1 plus 1 is 0, carry the 1 over here. 1 plus 1 is 0. And, what happens to that last one, since we only have 4 bits? We throw it away. Okay? So adding -5 and +5 like this won't work because we end up with -5 plus +5 is equal to +2. That's kind of a terrible math. That's terrible math right over there. So instead, they're like, okay, so we need a scheme that basically, if we do positive and negative numbers, they'll nullify. So let's put +5 over here. And the way we can nullify these numbers is just by making the negative version the inverse of that number, the binary inverse. So let's go ahead and put 1, 0, 1, 0. And we'll let all 1s or all 0s be equal to 0. Right? So here, this is -5 because if you flip all these things around, you get +5. So now we get 1, 1, 1, 1, and we'll interpret that as 0. But then somebody went to going, wait a second, that's kind of wasteful. We're using 2 combinations to represent 0. We don't have a +0 and a -0. We just have 0. So the way everything works for storing binary numbers is something called 2's complement, which simply means to figure out what the negative number is, we flip everything and add 1. So we create the inverse, we flip everything and add 1. So 1, 0, 1, 0. And then add 1 to this. And now what happens when we add these things? 1 plus 1 is 1. Sorry, 1 plus 1 is 2, right? So that's 0, 1, you carry the 1. 1 plus 1, 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0. And 1 gets carried and thrown out. Okay? So that's pretty cool. All right, so that means as a result, so the biggest number we can hold here is 7, right? This is the biggest positive number we can hold here is 7, right? Because we can't use this as positive negative. So if we go ahead and add 1 to this, we do 1 plus 1 is equal to 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. And we end up with this number. What is this number? So to figure it out, we flip the signs. We have to flip the signs. So sorry, we add 1 and flip the signs. So add 1 to this, flip the signs. So we get this number, which is -6. Well, actually, sorry, we get this number. Then this number is, sorry, messed up that. I don't know why. So to figure out what that, sorry, messed up. Forgot how 2's complement works for a second. To figure out what this number is, we flip the signs and add 1 to it. It's never in reverse. Always flip the sign first and add 1. So the real value for this is 1, 1, 1. So this is, I think, -7 or -6. I can't remember off the top of my head. I think it's -6. But anyway, the point is that this is something called overflow. And what happens is and that's what happens over here, just on a much larger scale. And this actually becomes a huge problem in programming sometimes. So how many of you have played Civilization? Right? A lot of you. Ever notice that in the modern era, if you're playing against Gandhi, he decides to nuke the heck out of you? This has been intentional since Civilization 2, where it was unintentional. Okay? So what would happen is that Gandhi, as we all know, is a pacifist, right? That was one of his big things, and that they encoded that in basically the video game as well. That basically he would, that playing in Civilization, you take control of basically a civilization and their armies. So Gandhi obviously doesn't like declare war, so his hostility rating, let's say, was equal to 0 for his AI. Okay? And this was stored in a byte, which is the values 0 to 255. And it was all positive, by the way. They didn't have any negative numbers, so It was all positive. So just a whole bunch of zeros for Gandhi's hostility. Well, once the AI adopts democracy, they also like to say, okay, if a computer adopts democracy as their ideology, then we should, and the form of government, then that should reduce the hostility of the government. Makes sense, right? Well, that would bring Gandhi's hostility to -1, except that, again, we were dealing with just pure positive numbers. So it wrapped around the other way and brought his hostility rating up to the maximum of 255, which meant that basically in Civilization 2, as soon as Gandhi adopted a democratic form of government, he became he basically became an Attila the Hun level warmonger and started deploying nukes and tanks and everything. So this happens a lot of the time in programming, and it was just one of those unintentional accidents. And they basically encoded it as an Easter egg in a lot of the remaining games. But this kind of thing, that's one of the more amusing things where an overflow can happen. So I'm going to just... All right, so that's it for today's lecture. I'll add a correction to the 2's complement, since I seem to have forgotten it off the top of my head. But that's what happens when I go on the side about it. All right, we'll go back into this on Wednesday. On Wednesday, you can expect a quiz in class on just evaluating expressions.